with the new design kit, there's a lot of things that we can actually explore. For example, the Monte Carlo, the process corner, so everything is automatically set up. You also get to realize the full potential of the tools. And Cadence is actually the de facto tools used by the back-end engineer in the industry. Used to be their competitor like Mental Graphic. I think Synopsys still dominate in terms of the digital synthesis, but back-end like place and route and also the mixed signal RF design, I think it's still dominated by Cadence. Okay, all finished scanning. Good. I apologize. After the first lecture, I've been disappearing for 1.5 months. I suffer from heart attack. Just completed 2 surgery, literally heart attack. So bear with me. I don't know. This is actually the first time I come back and give 3-hour lecture. I don't know whether I can make it. So if cannot, just bear with me. Also, I tend to speak softer. If you cannot hear me, let me know. Okay? I try to control my speed. I no longer can get agitated. So I try not to speak so fast. Bear with me. If you felt the tone is monotonic and too dull, let me know. Okay? I'll try to see whether I can change the tone a little bit. Now, the first lecture, we talk about IC design in general. More importantly, we talk about the device. We also talk about the matching concept. Okay, the matching concept. In fact, during the workshop, you probably have experienced something called offset. We simulate how to actually estimate the offset for op-amp. Now, the offset for op-amp mainly arises from the mismatch between the 2 differential devices. Okay, so we don't know how big the mismatch is, but the simulation, they already capture the model, so we can easily simulate it. Okay? Now today, this lecture is going to be very fundamental. We will talk about how IC designer can actually quickly look at the circuit and know how to dissect them and easily analyze them in a manner, writing down the gain expression or the equivalent impedance. There is nothing magical here. People are able to do that because they analyze them in detail and memorizing the result. That's it, to put it simply. It might look very magical if some people try to solve differential equation. They look at x squared, they right away write down 2x, magical. They look at sine x, they write down cosine x, magical. But that is because the mathematics teacher has already derived them, or mathematician derived them, summarized them, analyzed them in detail, and the students simply use it. So in circuit design, we are going to adopt similar approach here. So this lecture, we are going to focus on driving point concept. Very important. In circuit, driving point concept means that which point am I looking into? Why looking into? Because at that point, I'm driving this point with certain voltage. And I'm observing how much current is being drawn. That's why we call it driving point. I drive that point with certain stimulus and then observe how it responds. And because of this stimulating and responding, we are able to deduce some interesting relationship. For example, what is the impedance, equivalent impedance? And that allows us to simplify a network no matter how complicated it is. We are able to simplify them. And this simplification leads to easy way of analyzing a complicated circuit. We are going to illustrate to you step by step. So after introducing the driving point concept, we are going to focus on single stage amplifier. As mentioned, we zoom in, study in detail all the single stage. Once we finish with single stage, we further look at 2-stage amplifier. What are the important interaction between them? Once that is covered, more or less, you should be able to deal with most of the circuit that you encounter. Okay? So that is going to be the outline for today's lecture. So I mentioned this. It might sound magical to some of you or a lot of you when you look at the IC designer, circuit designer, they look at the circuit, they right away say, oh, this is what kind of amplifier? The gain is GMR multiplied by something. It sounds magical, but simply put, there is nothing. They just memorize the result. So if you still recall, when you first learn about differentiation, it's actually quite mathematically tedious. You are being introduced the limit concept. For example, to find the derivative of x squared, the teacher actually tells you, let's assume the x fluctuates by a little bit, delta x. And then you try to find the delta y divided by delta x. That becomes the gradient. And of course, you have to go through all this expansion, manipulation, with the assumption that the fluctuation, the delta x, is going to approach 0. When the delta x becomes 0, equivalently, you are finding the gradient at that particular point. So that is the concept. And we go through a bunch of derivation, and we tabulate some of the well-known results. For example, polynomial xn, the x to the power n, after derivative, it becomes n multiplied by x to the power n minus 1. Sin x, after derivative, it becomes cosine x, so on and so forth. And next time, when you are asked to actually solve differential equation, you are given any differential equation, you no longer embark on the limit concept. You don't go through the derivation on the left-hand side. Instead, you directly apply the table and write down in one sentence what is the result. That is the mathematical concept. Circuit, we do the same. Okay? So here, don't worry about this table, we're going to cover it. So we are able to analyze the result looking into certain terminal. For example, I look into the gate of the MOSFET. I know the equivalent impedance infinity. I look into the drain terminal of the MOSFET. What is it equivalent to? R0. So all this result, why we got all this result? We derived it before. And after deriving it, we tabulate them. After tabulating them, we memorize them. And then from here onward, suppose you are dealing with a more complicated circuit, what do? So with this more complicated circuit, we first start asking ourselves, who are the main character? So among all these transistors, maybe there is M4, that is the transistor that is responsible for all the signal path. Is responsible for amplification. Okay, so on and so forth. So this is the centerpiece. Now, if this is the centerpiece, all the surrounding are supporting actor or actress, right? They are playing supporting role. If they are supporting role, do I need to replace them with hybrid pi model of the transistor and start deriving the detailed equation? We don't have to, because we already tabulate the result. So we start asking ourselves, from the perspective of M4, okay, standpoint of M4, I look up into the M2, drain terminal. That is what we call driving point. Okay? From the M4 perspective, I look up, I see drain of M2. What is it equivalent to? It's no longer a transistor. I can simply replace them with a simple resistor, R1. I can derive this R1 using the tabulated result. Similarly, I look into the gate terminal of the M4. Okay? And I see from the gate terminal of M4, I look into M3. What am I seeing? Equivalent driving point. I can also replace them with R2. And same thing for M6. Once you did that, you see that the complicated circuit consists of a bunch of transistors eventually reduced into just the centerpiece, M4. And the surrounding is all just resistor. And that makes your life much simpler. Okay, eventually you also don't need to replace M4 with hybrid pi. You can still make use of the table and make sense of the result. That is the principle for circuit analysis. I wouldn't say it works 100%, because once in a while, there will be circuit that is hard to decide where is the driving point. even you are able to decide the driving point, it's hard to know which result can I use, because maybe the result hasn't been derived before. Can you guarantee that you have seen all the differentiation equation? All the functions that have derivative, have you seen it? If you still remember, I remember in my first year there is this engineering mathematics, so thick. There lists a bunch of differentiation table. And the most commonly used one, exponential x, sine x polynomial. Can you recall what is hyperbolic tangent differentiation? Probably not, right? So there are many, many functions that are listed down there, but it's not common to us. So we seldom use it. So I wouldn't say this approach is 100% foolproof, but it does get you almost 80-90% of the time. Okay? It can help you solve the circuit in an easy manner. So let's start. Remember, we deal with two transistors, BJT and MOSFET. So for BJT, let's start with the simple one. Of course, with a simple transistor, BJT, it got 3 terminals. So asking ourselves, for the BJT, let's say the collector is grounded, emitter is grounded. Of course, this ground doesn't mean really ground. It just means AC ground. Okay? You know that a transistor with the collector really connected to DC ground, it means nothing. Right? It's meaningless. But in AC analysis, if it's connected to DC voltage, eventually it's considered as AC ground. So suppose this transistor, we have emitter and the collector AC grounded, and we are looking at the driving point, looking into the base. What is the equivalent resistance? In fact, we don't have to derive, because you recall hybrid pi model. Hybrid pi model for BJT look like this. So if this is grounded, what you see is simply R pi. It's a hybrid pi, right? R pi. So what is R pi? Here I use Ri, but it's basically R pi. It's simply given by beta over Gm. Okay, so that is done. We don't have to derive. It's hybrid pi model. Same thing, if I have base grounded, emitter grounded, I look into here, this is R0. If this is grounded, no voltage over the resistor, so the current source, basically no current. So you can open circuit the current source, and you only see R0. You only see R0. So therefore, the driving point of the collector terminal is simply R0. Now the emitter side is a bit complicated. It's not that easy or straightforward to see. So since it's not straightforward, we have to fall back onto the fundamental. So let's do this. We don't know. Base is grounded, collector is grounded. I look into the emitter. What do I see? So if I don't know, remember what we told you, driving point. If I'm interested in looking into that point, I apply a stimulus, a Vx. I try to find what is the corresponding current drawn by the circuit, Ix. Now the relationship Vx over Ix, that is telling you how the circuit responds, equivalent resistance. So that is what we do. The transistor, we replace it with hybrid pi model. We apply a test voltage Vx, and then we examine the current Ix. Now, before we jump into writing down the equation right away, so this is Vx, so actually this is also plus negative Vx. Okay, so this is plus negative also Vx. Now this is a current source, but what this guy means is negative Vx. So negative Vx, I can actually change the current actually going outward, so it becomes positive GmVx. But it looks like not really a current source, because the current is proportional to the voltage applied across it. So this is actually equivalently a resistance, Ohm's law. A current voltage relationship, linear relationship, that is resistance, Ohm's law. So the equivalent resistance is simply 1 over Gm. So after removing the current source, what do I have? I actually have 3 resistance in parallel. Ri parallel with 1 over Gm parallel with R0, this guy. Now of course, if you are familiar, if you have done your tutorial 1, or if you have done many fundamental second year circuit analysis, you will know Gm usually, 1 over Gm usually very small. maybe a few 10 ohms or a few 100 ohms. Ri usually a few kilo ohm, R0 a few 100 kilo ohm. So when you parallel the tree, eventually smaller one dominate. So you end up having 1 over Gm. Okay? So we already derived 3 driving points. Looking into the base, looking into the collector, looking into the emitter. Now, there are other different things. Because the tree terminal is a very simple way, they don't connect anything. All the other 2 terminals just grounded. But life is not that simple, right? So for example, the first reflection rule, I have a resistor connected at the emitter side. Okay? So not really ground, but I have a resistor. And then the collector is actually grounded. So based on this guy, again, this is the first time I encountered it. So I have to actually replace the transistor with this hybrid pi model. And then we start deriving, applying the stimulus Vx, observing the current Ix. And of course, I can go through the algebra. So you can see here, I list down the algebra. What is Vx equivalent to? It's equivalent to V1, okay, this guy, plus the potential drop, Ix Ri. And what is Ix? Ix is simply given by this current, subtract away these 2 current. Okay? So I can list down all these equations, manipulate the algebra, and eventually I can end up having this result over here. But let's do some smart thing. Instead of deriving, so let's consider this guy. Actually, this is the input terminal, Vx. Okay, there is a drop here, and it gives you the V1. Okay, you know that the current going here is actually IB. The current that going into the RE is actually IB multiplied by beta plus 1. So effectively, it seems like in order to get the voltage over here, what I have is IB multiplied by Ri plus beta plus 1 IB multiplied by Re. And that will give me Vx. Quite straightforward, right? Because I know what is the current in the base junction. I know what is the current going at the emitter resistor. And to figure out the voltage drop is simply Ohm's law. I figure out the voltage drop across the resistor Ri. I figure out the voltage drop across the resistor Re. So I can do that. But IB is basically Ix. IB is basically Ix. So I can quickly derive Vx over Ix simply equals to Ri plus beta plus 1 Re. So I don't have to derive very detailed algebra. Just understand from the Ohm's law, I can actually easily derive the result, which is actually similar to this guy over here. Okay? So this is exactly what I'm doing over here. Okay? We still go back to the same result here. In fact, we call this kind of circuit series feedback. Series feedback. Why? Because this is actually a feedback register. It tries to sample the output current. After it samples the output current, it tries to feedback. But the way it inserts the feedback is in series with the input. So we call it series feedback. Okay? So with this series feedback, actually the observation is it boosts the input resistance. You can see that without Re, the input resistance is Ri. But once you insert this resistor, it's being boosted to beta plus 1 Re. So this series feedback helps improve the input resistance. So not only knowing this reflection rule allows you to observe the driving point, it also gives you something desirable. Suppose I want to boost the resistance looking into the base terminal. What can I do? I can insert the resistor at the emitter terminal. Okay, so it gives you something to think about and to do. Let me catch my breath. reflection rules number 2. So same thing, you have this transistor, collector is grounded. Now you have the resistor connected at the base terminal, and you are asked what is the equivalent resistance or driving point resistance looking into the emitter terminal. So if you don't know anything better, you can just apply a test voltage Vx and derive the corresponding Ix current. Okay? But here, we try to do something probably more intuitive. If this is the voltage, you can see this R0 is directly parallel connection with this Vx. So in fact, if I consider this whole thing as one whole network, I don't know what that is. But that resistance eventually is going to be parallel with R0 to give you Rx. You get the point? So if you identify the circuit, I look at this circuit, it consists of 2 portions. The top portion, quite complicated. But R0 is just parallel to Vx. So whatever that you can find for the top portion, let's say there is an equivalent resistance, that equivalent resistance is going to be in parallel with R0. And these two combined will give you what you see for the driving point, which is this result over here. Of course, from here you know that the top look like this. But how do we know the top look like this? So again, we can easily derive this. So Ix, based on the BJT, you already know Ix. This is IB. This is beta IB. So the Ix is simply beta plus 1 IB, but with the negative sign, because IB flowing down, but Ix flowing out. Now the IB can also be derived easily. Why? Because IB is basically your Vx divided by this resistance. So you can obtain the IB easily. Okay, so if you can do that, if you can know the IB easily, you can also know the Ix easily, right? It's basically just beta plus 1 IB, negative. IB you already know. You just put in IB here. Okay, and then you can easily derive Vx. So let me write it down. So this becomes negative beta plus 1 Vx, also negative RB plus Ri. So negative becomes positive. So you actually have beta plus 1 Vx RB plus Ri. So what we want is Vx over Ix. Okay, so Vx over Ix, now it becomes RB plus Ri divided by beta plus 1, which is this guy over here. Okay, so again, we don't have to resort to very complicated algebra. Okay, just some intuitive KCL, KVL. It allows us to solve this guy. And we can further split this guy because the RB plus Ri on top, we can separately divide it by beta plus 1. Of course, RB divided by beta plus 1, there's nothing we can do. But Ri divided by beta plus 1, Ri divided by beta plus 1 is approximately Ri divided by beta is approximately 1 over Gm. Okay, because Ri equals to beta over Gm. We derived that before. Okay, so we get this result. We get this result. There is reflection rule number 2. Finally, reflection rule number 3. So again, base is grounded. We have resistor connected at the emitter side. Now, by the way, all these derivation is kind of boring, I know. It's very dull. So what I try to do is that if you don't want to listen, it's fine. You can go back and then read through yourself how you derive this thing. Okay? It's simple algebra. I list down the step already. It shouldn't be too difficult to catch. What I'm trying to do here is trying to inject something, how people can actually, without going through the algebra, in a very easy manner, see what is the final result. So in the derivation, you can see that in some of the reflection rule, I show you. I actually don't have to go through all these. You can quickly equate these, and eventually through KCL, KVL, you can get the result. So hopefully it can bring you something interesting. How come circuit people can treat it that way? Okay? And if you learn many of these tricks, eventually it makes your life easier because you know all these tricks can be applied for circuit analysis. Now, reflection rule number 3, you have Rx over here. Your base is grounded, you insert the resistor at the emitter side. Now, frankly speaking, there is no trick here. I ran out of trick, so this one I really have to go back to fundamental, deriving all the thing in mathematics. So I replace transistor with hybrid pi. I apply a test voltage Vx. I try to find the equivalent test current Ix. So first, your V1 is simply, if this is Ix, this is also Ix. I hope you can see that. Okay? So V1 is simply Ix multiplied by these two resistors in parallel. Straightforward. Now Vx is simply V1 plus the potential drop across the resistor, R0. And what is the current going through this resistor? You know this is Ix. You just subtract away this current. And then you will be able to know what is the current going through R0. So that is how you derive the second equation. Okay? And then the rest is mathematics. Okay? Unfortunately for this one, I don't have trick. So you just have to go through the mathematics. I need to figure out relationship between Vx and Ix. And V1 is the intermediate variable I don't want. So I'll try to figure out a way to remove V1. So eventually, you end up having the following result. It's quite complicated, but looking at this one, right away we know something we can throw away, this guy. Because I know this guy cannot be bigger than Ri. Cannot be bigger than Ri. And Ri is a few kilo ohm, usually. The second term, R0. I know this one is at least R0, which is a few hundred kilo ohm. So compare the first term and the second term. I don't have to keep bothering myself with the first term. Right? It's like your pocket money, you have 2,000, but your bank saving, you have 2 million. What is your total asset? You don't go and tell people, my total asset is $2 million and $2,000. Right? It doesn't make sense. You just tell people, my asset is 2 million. Forget about the 2,000. That is pocket change. Right? So, with these two terms, you know which one dominate. You throw away the smaller one. Don't make your life miserable. Okay? So, here, although we didn't introduce any trick in analysis, but there are some insight I want to bring your attention to. Now, if you look at the equation, so forget about this guy, you see that the Rx look like this guy. So, let's analyze two cases. The first cases, assume Re smaller than Ri. So if Re is smaller than Ri, of course, the two parallel, you can forget about Ri. And the whole thing becomes R0, 1 plus Gm Re. So what this guy is telling you is that if you plot the x-axis with Re, if you keep increasing Re, you can hope to increase the equivalent driving point resistance looking down the collector terminal. So you can see this increasing trend. Now, in the second scenario, Re now becomes much bigger than Ri. Now, if that is happening, now you would be ignoring Re because now Ri is smaller. So you are going to end up having R0, 1 plus Gm Ri. But we know Gm Ri equals to beta. Why? Because Ri equals to beta over Gm. So in the end, you end up having this guy. You know R0 is constant. Beta is constant. So it tells you, inserting this guy larger and larger, you think that I can make the resistance looking down the collector terminal larger and larger. You are wrong. The maximum you can go is beta R0. This guy. Once you reach this guy, you keep increasing the Re, it doesn't help. Okay? So that is the limit. I mentioned this. Why? Because in cascode design, later we are going to visit cascode design. MOSFET, very useful. Use cascode two devices because this guy got R0. I insert the R0. So looking from the top, my resistance increase further. And then if this resistance is increased further, let's cascade another one. Looking down, it's going to be getting even larger. So you can actually get very large equivalent resistance looking down into the drain terminal for MOSFET. But for BJT, you seldom see people go beyond 2 cascade. Just 2 transistors stacking each other, enough. You try to stack another one, it doesn't help. Why? Because of this. Okay? Because of this. Now, I know some of you are actually my undergraduate student. So you probably see this thing already. So here what I'm trying to do, in order not to bore you, I try to bring some new insight. These are probably something that I never talk about because for undergraduate I don't need to. Okay? But these are the things when you look into IC designer, these are the things that people pay attention to. Okay, I want to cascade many devices to boost the output resistance. But why BJT? No people do that. Because of this. Okay? Okay, last rule. So, reflection rule, number 4. You have the RC connected at the collector terminal. Your base terminal is grounded. You are trying to find the equivalent resistance or driving point resistance looking into the emitter terminal. So you end up having, have to derive it from the fundamental again, this guy. Again, there is no trick here, okay? I don't have any trick over here. So let's derive. So what is the Ix? Ix is simply given by this current, which is this guy, this current, which is this guy, and then this current, which is given by this guy. And what is V1? V1 is simply Ix subtract away this current. So now I get the current flowing here. And this current will flow through RC to give you V1. So this is the second equation. Okay, simple algebra. Now with these 2 equations simultaneous, I know that I want to derive relationship between Vx and Ix. So all the intermediate variable, which is V1, I need to remove it. Okay? So after some manipulation, I end up having a complicated one, but already tells you Gm, okay, because 1 over Gm is much smaller than Ri, much smaller than R0. So Gm will be much bigger than 1 over Ri, will be much bigger than 1 over R0. So from this result, I can throw away these 2 right away. And then after some manipulation, I end up having this guy over here. Okay, this guy over here. So now, let's draw some insight. Let's draw some insight. So if RC, let's say there is no limit, I can put any RC that I want. Okay, I can put any RC that I want. So I can put any big RC that I want over here. If you simplify it, if RC is so big, I forget about R0. So RC cancel, the whole thing simplified to beta over Gm. So that actually tells you what is the maximum resistance you can see looking from the emitter terminal. This guy over here. But just now we have derived a very interesting result. Okay, if I decided the whole circuit I don't use resistor, I use BJT. And you know that what is the maximum BJT resistance you can see? Beta plus 1 R0, isn't it? Okay, so if I replace RC with beta plus 1 R0, what am I going to get? So this is beta plus 1 R0. Okay, so this thing roughly equals to beta R0. The bottom one, okay, this is beta R0, so this guy cancel, it becomes 2 R0. Okay, R0 cancel, so you get 2 beta over 2 Gm. So this is the result. Beta over 2 Gm is what? Beta over 2 Gm is simply Ri divided by 2. Okay? So this tells you, if your circuit is built purely with BJT, not register, you register, you can get any RC you want, right? The maximum RC is infinite. But if you build every circuit with BJT, you know that for BJT, the maximum resistance you can look into the collector terminal is beta R0. If that is the case, the maximum value that you can get is basically half Ri. Okay? Okay, we're done with MOSFET. We're done with BJT. Now, MOSFET is actually quite similar to BJT cases. So, first thing, the gate infinite. Very simple. Look into the gate. It should give you open circuit infinite. Looking into the drain terminal, you also know R0. Okay, except that this output resistance equation is governed by lambda, not early voltage. So 1 over lambda ID. Okay? Now, looking into the source terminal with gate grounded, drain grounded. So for this one, we have to derive it. So if I apply Vx over here, the Ix over there, now we can do something similar. So the voltage across this guy is actually Vx, so it's R0. The voltage across this guy is actually Vx. The voltage across this guy is actually minus Vx, so actually the current is going up. So equivalently, I can lump these two together and make it an equivalent resistor, 1 over Gn minus Gmb. Right? Because although it looks like a current source, but think carefully. If I say this is a current source, which is GnVAB, this is A, this is B, then this is actually equivalent to a resistor 1 over Gm, the current AB. Both will give you the same current, am I right? Okay? So don't be fooled by the current source symbol. The current source symbol only meaningful if the voltage is not at the two terminal. If the voltage is actually at the same two terminal, it's a resistance. This is Ohm's law. So with that, I see that this is basically just two resistors in parallel. 1 over Gm minus Gmb parallel with R0. And then eventually you get the following result. Okay? Now, the first reflection rule, MOS have fewer reflection rule. So, my gate is grounded. I inserted something at the source terminal. What is the equivalent resistor looking down into the drain terminal? There is nothing I can do. Okay, so I go back to fundamental. I replace everything with hybrid pi. I insert the test voltage, find the test current. So Vs, which is this guy, is simply given by Ix multiplied by this resistor, Rs, Ohm's law. And the Vx is simply given by the Vs plus the voltage drop across R0. And the voltage drop across R0 is simply Ix. Subtract away these two current. Okay, so that is the result. After some manipulation, again, we end up having this simplified one. So unlike BJT, you see that it is directly proportional to the resistance inserted at the source terminal. So ideally, or in theory, the larger the RS, the larger the drain equivalent resistance or driving point resistance that you can get for MOSFET. Okay, simple as that. So ideally, you can extend this guy infinite. And that is the reason in MOSFET, if you want higher resistance, you will see 3 transistors in cascode. Some say not sufficient, 4 transistors in cascode. Okay, there are people cascoding many transistors in order to boost the resistance. But eventually, what limit the diode? I don't know whether you guys still recall my first lecture. I did draw the MOSFET, right? I did draw the MOSFET. This is gate. And then this is N plus. This is N plus. This is drain. And this is source. And this is the P substrate. Okay, the P substrate usually is grounded. So let's assume this is grounded. And you notice that this is actually a diode, isn't it? Right? Now, for all practical purpose, let's say transistor is operating, usually it draws current milliampere. And since the diode is reverse bias, usually you only draw current nanoampere. So do you care about this diode? You don't care. Reverse bias diode, as long as it doesn't break down, it's like open circuit because the current is so small, right? But now, if you try to make the resistance so big, let's say the resistance is reaching gigaohm. You want to create such that the resistance is equivalent to gigaohm. So think, when I look into here, I want Rx to be approximately gigaohm. What does it mean? It means that if I apply 1 volt, it should only draw nanoampere. Am I right? Okay? Now, what if I'm not happy? I want it to be 10 gigaohm. It means if I apply 1 volt, it should only draw 100 picoampere. Am I right? But how much did the reverse bias diode draw? Nanoampere. Right? So there is a reverse bias diode here that is already drawing nanoampere. So are you able to reach picoampere? Never. You can never able to reach picoampere. Because although this branch can give you picoampere, the diode branch gives you nanoampere. In total, you still end up nanoampere. But equivalent resistance is how much current draw at this point. So the two have to sum together, which means no matter what, eventually you are going to be limited by nanoampere. So nanoampere is how much? Gigaohm. Which means your resistance is going to be saturated. You can no longer go bigger. It's limited by diode. Gigaohm. So in theory, I can cascade more transistor to get higher resistance, but in reality, nothing is free. Okay? Nothing is free. Reflection rule number 2. So I connect a resistor at the drain terminal. I look up into the source terminal. Gate is grounded. So again, I have to start from the fundamental. Replace transistor with hybrid pi. Connect the RD over here. Connect the VX over here. So let's figure out the expression. The IX is simply given by the current source plus the current going through R0 over here. And then the V1 is simply given by, this is IX. IX multiplied by the RD, Ohm's law. And after some mathematical manipulation, you see that it ends up something very similar to BJT, this guy. Okay, what is BJT cases? BJT result, if you recall, 1 over GM, R0 plus RC, R0 plus RC over beta. And in fact, you can easily derive this result based on BJT. What is the beta for MOSFET? What is the beta for MOSFET? If we define beta as IC over IB, then for MOSFET, we can do something similar, ID over IG. But what is IG? 0, no current. So which means this guy becomes infinite. So if you put infinite over here, this guy disappears. Therefore, you end up having this thing over here. And why there is a GM minus GMB? Mainly because of the body effect. If there is no body effect, you don't care about GMB, it reduces to similar thing as the BJT. Okay? Great. We have completed all the driving point equivalent. So if we summarize the result, now you are able to just look at which terminal and then see whether there is resistor there, you can easily derive the equivalent resistance. Okay, that is the first step. Now, transistor, most of the time we try to use it as a signal processing circuit or mainly amplifier. So in that sense, usually we would know there would be input connection to the transistor and where the output connection connected to. So for BJT, for example, there are different ways of connecting. input going into the base, output coming out from collector, input going to the emitter, output coming out from the collector, input going into the base, output coming out from the emitter. So 3 different types. For the MOSFET, same thing, gate, source, drain. So it depends on where does the input go in, where does the output coming out from. So there are 3 different connections, and based on these 3 different connections, you can give it a name. So if input go through base, output go through collector, emitter is neither input nor output, we call it common emitter. Any terminal that is neither connected to input nor output, we call it common. Okay? So let's start with first stage. Now you have the resistance, okay, the driving point resistance. We no longer need to go through the tedious hybrid pi model. We can actually easily derive this guy. Okay, if you are skilled, you can even write down, looking at this guy, you can right away write down this thing. Okay? I'm not kidding. It's possible. You can look at the circuit and write down this guy. So first thing we do is, what is the equivalent resistance looking into here? So first, let's do some AC analysis. So for AC analysis, all the voltage source short circuit to AC ground. The capacitor should be short circuit. So this circuit will be transformed into the bottom one. But if you are skilled at this, there is no need for you to transform from the top to the bottom, because capacitor in your eyes, short circuit. DC voltage source, short circuit to ground. Have you watched a movie, Matrix? Yes or no? Matrix. So the actor, look at all these scenarios, what did he see? 1 and 0. Okay, so same thing for circuit designer. If you are so skillful, you no longer see circuit. All you see is ground, short circuit, equivalent driving point. That's it. So, looking at this guy, first thing, what is the equivalent resistance looking into this? You will see that it is basically RA parallel RB parallel. What am I looking into? Base terminal. Right? If I'm looking into the base terminal, I know the answer, Ri. So therefore, the input resistance is simply given by this guy right away. RA parallel RB parallel Ri. How about output? Now for output resistance, I'm looking into here. Now if I'm looking into here, what do I see? I see the top, RC, and then the bottom. The bottom is looking into the collector terminal, which is R0. So R out equals to this guy. Right away, you get the answer. How do you derive the gain? Now derive the gain. If you look at the signal path, starting from Vs, it goes through here, and eventually reach V out. So along the signal path, what does it go through? From Vs, you will reach V1 first. But to get the V1, I can easily use this concept, right? I already know the Rin, I already know the Rs, and this is Vs. So this is V1. So to get the V1, I only have to use voltage divider. Am I right? So that is how I get voltage divider. And getting V1, how does it help me? Getting this V1, it will directly control the current source. Because any voltage appear at the base, the emitter is grounded. So this guy will directly control the current source, GNVBE. So, GNV1. Now this current source have to flow through some resistance. What resistance? The output resistance. And don't forget, finally there is this RL. And they are all in parallel. So, although I break it into the few steps, first I obtain V1 through the voltage divider, and then I obtain the current source using GNV1. Finally, I use Ohm's law, the current multiplied by the total resistor to give you the final output voltage. But all these can be combined. If you do this a few times, you will see, oh, very easy. Let's determine Rin first. Once I get the Rin, I can write down voltage divider. And since this is common emitter, we are going to have GM cell, current source. And then finally, the output resistance is basically, where is your output point? Your output point is here, V out. And you stand at this point, you look around 360 degrees. What is the resistor that you see? Top, RC. Bottom, R0. Right, RL. So, this guy. Okay? So you can easily derive the gain in one shot. Now, of course, there is polarity issue. So polarity usually is a big issue. Student is confused. Should I put negative? Should I put positive? Now, my simple answer is that if you are first time encounter this, of course, you need to make everything right. You have to see where is the current flow direction. Eventually, you derive everything correctly. But this is not the first time you see it. Okay? After this lecture, next time you see it, that will be the second time. Right? So, you already know this is common emitter. There will be a negative sign at output. Just commit to your memory. Common emitter, gain is negative. And the numerical value you can derive easily. Just the polarity sign. Common emitter, negative. That's it. Right? So this is what people call early T amplifier. It was first invented for video amplifier. Now, circuit has been exist for many, many years. So a lot of you probably forget how far we come. In the old days, when people still use the cathode tube, have you heard of the term called cathode tube? Right? A very big screen, glass one, right? But it's like this thick, right? And then you try to emit some not gamma ray, some ray, I don't know, electron beam or whatever, and you shoot the screen, right? So when you shoot the screen, the picture got shot, right? So in order to do that, you have to design some amplifier that are able to respond quickly, right? So people at that time, before the television, people actually have to scratching their head. How can they come up with amplify the signal, but fast enough? What kind of bandwidth are we talking about? 6 megahertz. That is old analog television standard. Okay, 6 megahertz bandwidth. So your amplifier need to be able to sweep that fast. Of course, nowadays, we are talking about gigahertz. But remember, when the transistor first invented, this is actually a struggle. And this amplifier actually able to do that. Early T amplifier. So what is the characteristics of this amplifier? First, there is a negative gain. Now here, I need to bring to you, in amplifier term, negative doesn't mean loss. Okay, amplifier, you have negative, it doesn't mean loss. All it means is phase inversion. Okay, if your signal is positive, you end up having negative. If your input is negative, you end up having positive. Everything gets inverted. Okay, but as long as the number is bigger than 1, you have gain. You have gain. So, in polarity inversion. And this amplifier is able to give you medium gain. Only one stage, medium gain. And the characteristic is, it gives you moderate Rin. You cannot say it's high because it's going to be parallel with Ri. Even you are able to pick very big Ra, Rb, eventually it's limited by Ri, which is a few kilo ohm. Okay, so moderate. Rout. Okay, Rout. If you are able to pick big RC, then your RL can be big because R0 is a few hundred K. Okay, gain high. I would say moderate gain, not high gain. And one of the drawback of this amplifier is the so-called Mueller effect. Mueller effect. And this effect is dominant if you have big RS. Big RS. We are going to revisit this. So one of the issues suffered by this guy is actually Mueller effect. And it's quite dominant. You will see it everywhere. In fact, baseband amplifier will mostly use it, right? Even some RF amplifier, some people actually don't care they use it because it's very simple. Very simple. RF amplifier, one of the key requirements is actually impedance matching. impedance matching. We need to match to the antenna 50 ohm. So the amplifier have to present a 50 ohm resistance. Now you might be thinking, that is easy, right? 50 ohm resistance. But for RF amplifier, you want to do it without introduce too much noise. And you know, with resistance, it comes with noise. You cannot avoid that. But some people don't care. So what they do is, I have this amplifier, just terminate this with 50 ohm. Okay, it's a very simple design. So people do use that if they don't care about the noise. Why? Because with a 50 ohm fixed resistance, you guarantee wide band matching. No matter what, it's always matched. And those people scratching their head using inductor to match or using a transistor to match, they can reduce the noise, but they are dealing with something else. Inaccuracy in matching. They might not be able to get 50 ohm. Okay? Am I too fast? Am I too soft? Okay, good. Let's look at Mueller effect. You guys probably heard of this guy very often. Okay? So what does it say? Mueller effect basically tells you this. If an amplifier have a negative gain, minus A, I stress this, it must be negative gain. Okay? If it's not negative gain, you are going to have positive feedback. Because you connect the output back to the input, you are going to have positive feedback. You know positive feedback. I know that you guys like positive feedback. I also like positive feedback. But unfortunately, circuit don't like positive feedback. Right? Why? Positive feedback mislead you into thinking that you are good. Right? So positive feedback is like you do something well, we say, oh, you do very well. And then you think you do very well, so you just keep adding positive feedback. Eventually you think you do fantastic, but in the end it's not. That is positive feedback due to you. Okay? So negative feedback do the other way, right? It makes you more cautious. You do something, you say, no good, don't do it. And then you try to tone down, no good, tone further. So eventually you don't dare to do anything. That is negative feedback. But circuit will like that. Why? Because cautious. It don't give us any harm. It try to stabilize everything. We like something stable. And in fact, I do joke around. The COE system in Singapore, positive feedback or negative feedback? COE, you don't know COE? I used to joke around. The COE system in Singapore is actually positive feedback. It makes everything unstable. Think about that. COE price go up. Nobody wants to sell the car. Supply get limited. The price go further up. Positive feedback, right? Maybe you can come up with something called negative feedback. Now, Mueller effect. Amplifier is negative gain. Now, if you have an amplifier that is negative gain, if you try to connect a component from the output back to the input, that is what we call shunt feedback. Shunt feedback. What does it mean by shunt? Earlier we examined the series feedback, where the feedback component is added to the input in series. This guy, you see that the feedback is added to the input in parallel. Do you see that? The feedback is feedback in terms of current branch. I'm feeding back, adding it in parallel. There is still this guy here. Okay? So when this is shunt feedback, the effect is actually reducing the equivalent impedance. Equivalent impedance. And reduced by how much? Reduced by the gain. Reduced by the gain. So suppose you have the resistor R connected between the output and the input. Then the equivalent impedance is simply given by the R divided by the gain, 1 plus A. So we can see the equivalent resistance reduced. The equivalent resistance reduced. This is actually what we call trans resistance amplifier. It's very popular amplifier for optical network. Optical network. You know, optical network, a lot of time we are using photodiode. The light shine on it, it will start to generate current. you start to generate current flowing through. Now, if you have this kind of trans-impedance amplifier, okay, you are reducing the equivalent resistance looking into it. So it doesn't matter, let's say there are some other thing connected over here, you know current prefer to flow to the smaller resistance. Am I right? Suppose there are other things connected over here. But because of this, trans-resistor amplifier is presenting R over 1 plus A. It's making the resistance A times smaller. So it's like student. Student always choose the least difficult subject. Am I right? Human nature, right? So I don't understand why you choose this module. Right? So current, same thing, human nature. Current always flow to the least resistant part. So trans-resistor amplifier, by reducing the resistance, it encourages the photodiode current to go through it. Okay? So this is a very popular form of optical amplifier. Now, what we want to focus on is not on this. What we want to focus on is the very infamous thing called Mueller effect. So imagine, instead of feeding back using a resistor component, you feed back using capacitor component. Now resistance is nice because resistance, it reduces the equivalent resistance by A times. But don't forget, capacitor impedance is given by 1 over J omega C. If you reduce the capacitor impedance by 1 plus A times, what does it mean? You are increasing the capacitance by 1 plus A times. Am I right? So that is what makes it infamous. You know, a lot of time, capacitance determine the frequency response. Right? If you want to go to high frequency, you want the capacitance to be as small as possible. Agree? Higher capacitance, larger capacitance don't give you high frequency response. It limits the bandwidth. So this Mueller effect make the capacitance worse and therefore cause the equivalent resistance, equivalence dominant pole to be smaller and limit the bandwidth. That is what makes it infamous. Having said that, it's not all bad. It's not all bad. There is scenario where you want to build filter and you want to build the cutoff frequency very, very small. What kind of scenario? I just have heart attack. So this issue is dearest to me. Why? ECG. You are measuring your ECG. ECG signal is at what frequency? 100 Hertz. Right? You want to design a circuit that is operated at 100 Hertz. You need very big capacitor. Agree? But big capacitor means what? Area. But Mueller tells you you can get 8 times larger capacitance with just the same capacitance. Right? So it gives you the moral story. Not everything is bad. Even the worst thing, that might come in handy sometimes. Okay? So Mueller effect, people do use it to boost the capacitance, especially in filter design. Okay? If you want large capacitor, no way to go. I want to boost the capacitance by 100 times. Mueller effect. You just have to design an amplifier that is 100 times gain. Now, another common mistake that students make for Mueller effect. So you look at the bottom one. Bottom left and bottom right. Only the bottom right suffer from Mueller effect. Because in terms of pole, a simple thing, if you want to form a low pass, capacitor alone cannot do that thing. You always need RC, because the bandwidth is given by 1 over 2 pi RC. You always need the R in series with the C to form the pole. Without the R, the C alone, useless. So a lot of time people talk about Mueller effect. I remember my supervisor told me, this is a very popular question come out during interview. So circuit design company, they will ask the candidate, they show you the circuit. Can you describe what is the effect of C mu? So a lot of students will just answer, oh, Mueller effect, I know, Mueller effect. But this guy actually no Mueller effect. If the guy show you this thing without RS, without resistance, there is no Mueller effect. Mueller effect doesn't exist. They require resistance. Okay? I'm not calling it a stop. I want to do something here. Can you scan this guy? Can you scan this guy? Done? Are you able to see the question on your cell phone? Oh, haven't scanned. Done? Okay, are you able to see this on your cell phone screen? Get ready, huh? Okay. We have covered the driving point, so I'm going to ask you something. Let's move on. You have about 1 minute to answer this. The faster you are, the higher the marks. Should be easy, right? If you don't fall asleep. No? Especially those students who have taken my undergraduate module. I will hold you responsible. You should answer this correctly. Done? It doesn't matter. I'll wait until 1 minute. Total result 27, 29. Why suddenly drop? Okay, no more response. Good, most of you get it right. Okay, so there is BJT. So it means you do pay attention. Okay, so these are the leader. So the faster you answer, the higher the score. Now let's see whether I have second question. It's also related to RX. So there is MOSFET. All done? 24, 25. I think we should have 29, right? 30. Seems like all done, huh? All done? Okay. Correct. But a little bit drop. From 79% just now, drop to 70%. Okay? So why you say RX will increase with RS? I think I did mention, right? Eventually it's limited by diode. Now the diode is called leakage. Okay? Well, suddenly all gas. Okay, so this is the It's okay, you can refer to the lecture note. This one I think it will take more than 1 minute. Only 2? This is really tough. All done. So only 18 students respond. Now to solve this thing, first thing I'll notice, this is a diode connected transistor. So right away you know it should be 1 over GM Q1. So out of all these 4, you can ignore this guy right away. The second one right away. And then this is MOSFET and with body effect. So you can ignore this guy again. So you need left with the last 2. Right? But for this guy, we have to look at M1 R0. So it has to be this guy. So the third one should be the correct one. It doesn't take you too long. For multiple choice, usually it doesn't need to take you so long because you can use reject one by one. So eventually it will lead you to the correct answer in a very fast manner. Okay, I guess that's it, right? Okay, I think that is the total based on the 3, right? Oh, another one. Wow. I forgot how many I said. So try to use just now the logic I told you. One by one, rule out. You are looking into the emitter terminal. So you can rule out 1 already. Okay, this one better. We have more students trying. Now it's already 23, 24. Okay, 26 students, not too bad. A shock, only 19% get it right. What is the top transistor? The top transistor is 1 over GM. 1 over GM usually is very small. So R0 Q1 plus 1 over GM M1, you can right away ignore 1 over GM. So R0 cancel, you are going to end up having only 1 over GM Q1. So this one involves some deduction right away. Although the formula looks like the second one, but the second one, there is no R0 M1. It's 1 over GM M1 because the top transistor is diode connected transistor. Wow, finally we have 1%. It's no longer called gas 759. Okay, I guess that's it for this. I have another one we are going to try at the end of the things. But let's continue.